Hey everyone, today we're covering some work and heat concepts for common processes. So there are these four common processes that is used quite frequently. One is called isobaric process, in which dP is 0. So if you go from a point 1 to point 2, then the pressure change will be 0. Isochoric process, where in each step dV is 0, here each step dP is 0. And then there is something called isothermal process. If I go any step here, dt is 0 on that. And then there is adiabatic process, where you go any step, no heat is goes in or out of the system. Okay, you can think of these systems as there's a cover or a piston, and the system is inside here. This is where the gas is. This is the system, and we're moving this, or maybe we're putting heat in there. So this, by moving this, we do the work, and putting heat in there, or taking heat out, maybe taking heat out. So the Q in is positive when this thing is compressed. The W is greater than 0 if compressed. When the heat goes in, it's positive. So there's a notation for us. Okay, maybe you can try some of these, and this is an ideal gas. So if you look at any one point, so state is defined by how much pressure there is, how much volume there is, what temperature there is, and how much gas you got. And this we're going to use as moles. I know sometimes you want to use N, it will be number of molecules. Okay, and you probably know this also, that there is a relationship between this PV equals to N RT, and if you want to use number of molecules, you write the same thing as PV equals to N Boltzmann constant T. It's the same thing because R and Kb are related through in this manner. Okay. Okay, so what is the what's going to be work over here if we go from 1 to 2? We are going to do it very simply. Use our basic definition. In any small step, dP in point 1 to point 2, which is differential difference, is minus p dV, right? And when we integrate it, I'm going to get from 1 to 2. So W1 to 2 is integrate over this thing, minus p dV 1 to 2. And this is integration variable, so this will be V1 and this is V2. And on this process, P is constant, P comes out, minus P V2 minus V1 will be the answer. How much heat is involved, we'll talk about it once we get done doing this. So let me write down over here this answer. Maybe we can collect the answers here. W12 constant pressure case is minus P V2 minus V1. So, all right, so this is one isochoric process. So when I do this is small, so in dW is going to be minus p dv again. This is fundamental. But dv in this process everywhere is 0. So minus p 0 is 0. So even if p is changing, when I integrate it, integrate 1 to 2, p dv will be 0. So this is W12 volume constant is 0. Over here is the work will be, so if in a small step, P is a function of V now. So dW is equal to minus C over, C is defined to be this constant, C over V dV. And so when I integrate it, W12, when I integrate it, this integral will be V, so this is going to go from V1 to V2. So C will come out. This will be log V2 over V1. So when we have a V2 over V1, you can write it in a number of different ways. And so this is C is putting C back minus nRT log V2 over V1. So W12 temperature constant is minus nRT log V2 over V1. So if V2 is more than V1, it's going to be negative. I mean, if it expanded, it's going to be negative, like it's here. And if it's compressed, then this will be less than 1, log will be negative, and it's going to be positive. So if it's compressed, it's going to be a positive work. Adiabatic, adiabatic is a process where at each step, and there's no heat can enter the system. Okay, so if you look at a tiny step, the curve on which it goes is given by this in adiabatic. This is for ideal gas. This formula is for ideal gas. So if I have ideal gas and I do adiabatic process, so its pressure and volume must be related by this. So there's some constant B. You can, depends on where I started, so we can call it this. And the gamma is a ratio of Cp over Cv. Cp is specific heat at constant pressure, and it's a specific heat at constant volume. And if you work it out in terms of degrees of freedom, so this related with degrees of freedom is 3 for monatomic gases. So where the molecules are just one atom, is 5 for linear molecules, vibration not active, so the temperature is not too high, and then 6 for all others, vibration not active. So we're just looking for, this is a kinetic energy of Cm, so those 3 degrees of motion, and this is kinetic energy of Cm plus 2 rotational degrees of freedom, and this is kinetic energy of Cm plus 3 rotational degrees of freedom. Okay, but if the temperature is high enough, you will have to include the vibrations. Okay, and so these are not completely correct. They can change, but this is always the case because there is no rotation of vibration for this case. All right, so here the same thing, you know, you're going to be W12, and this is going to be minus P dV, and this is the volume, so it goes to V1 to V2, and P now is B over this, minus V1 to V2, B over V to the power gamma, and gamma is, you can see, greater than 1. It's greater than greater than 1. and so you have a dV, so minus B, you integrate, so V to the minus gamma, so minus gamma plus 1, and then V to the power V2 to the power minus gamma plus 1, minus V1 minus gamma plus 1. You can write this in, B is V1 V1 to the power gamma, so you can actually write this a little more. Let's this take minus with this minus, make it plus. So you have a gamma minus 1, and B is V1, and V1 to the gamma, we can just go down inside here. You have a V2 minus gamma plus 1, and you're multiplying with V1 to the power gamma, V1 to the power gamma, and this will be just V1, and you can see over here, there's a ratio of V1 to V2, and then so let's do it a little bit simpler. Gamma minus 1, so you can simplify it. So W1 to Q constant is actually P1 over gamma minus 1, V2 over V1 to the power gamma, and a V1 over V2, V1 over V2, V2 minus V1. So these are the answers we get for W, and now we want to talk about how we can say how much heat got involved in each one of the processes. Okay. So these are our answers for work. To get the heat involved, Q in this process, well, we can use first law. Since we have ideal gas. So in terms of first law, one thing to notice is U for ideal gas is simply depends on degrees of freedom over 2 N R and T for any state. You can put in there, and that there will be degrees of freedom over 2 times PV. So you can use either of these forms for ideal gas. So let's use that, as well as you have a delta U of a process, some 1 to 2 is Q in 1 to 2 plus W1 to 2. So we want this, and we can get this by just looking at temperature difference or PV difference. So let's look at isobaric process. So Q12 isobaric process will be delta U12 in isobaric process minus W12. So this one is going to be, let's use PV, dF over 2, P2 V2 minus P1 V1, that's for this, minus this guy, just minus with a minus becomes plus P1, let's call it P1, V2 minus V1, and P2 is equal to P1 because we have isobaric process. So we can write this as P1, and we can take the P1 out, and so this is same as that. So we just get a 1 plus dF over 2 P1 V2 minus V1, and okay, that's the Q. So for that, Q12 for that is 1 plus degrees of freedom over 2 P1 V2 minus V1. Okay, so that's done. Let's do this thing. And isochoric process, we have work is 0, so Q12 for isochoric process will, from this law, will simply be this is 0, so that's going to be just delta U12 isochoric process, and that just dF over 2 P2 V2 minus P1 V1. So now V2 equals to V1, so I can pull that out. So dF over 2 P2 minus P1 times V1, because this is now writing that to be 1 because this volume is same. Okay, so that's this is Q12 is dF over 2 P2 minus P1 P1 times just P1. So you can see all the formulas come out different, but the process is the same, right? Procedure is the same. So if you focus on just memorizing the formulas, you're going to be in sometimes big trouble. Okay, let's do this guy, number 3, the same way. For this, delta U will be 0, because if this doesn't change, the delta U of isothermal process will be 0. So that means Q12 using this isothermal process will be minus W12 for isothermal process, and we already got that answer. So that just for Q12 in this case is just minus with a minus, with plus nRT log V2 over V1. Finally, adiabatic process, we already have a Q equal to 0. So we can say, what is the delta U for this? Delta U will simply be delta U for adiabatic process simply will be W for that process, W12. And W12 was found to be here, is P1 over gamma minus 1, V1 over V2 to the power gamma, and then V2 minus V1. So let's say Q is 0, internally change is same as work done on the gas. So hopefully this clarifies some of the things that you have learned in classes, and I will stop here, and I'll see you in another video. Don't forget to hit the like button, because that helps us circulate this video. And maybe if you haven't subscribed, you can subscribe to this channel. I'm trying to post one problem a day. So next time the problem coming up is going to be is still thermodynamics. Okay, there are many more things to go, and we need to cover second law, entropy, and things like that. Okay, take care. Bye bye.